Download this code from codegive.com, link in the description below. Buffer Overflow ZAP tutorial, a deep dive with code example. This tutorial aims to provide a comprehensive understanding of Buffer Overflow ZAP, BOZ, a type of buffer overflow exploit targeting applications compiled with the ZAP compiler. We'll cover the fundamental concepts, how ZAP affects memory layout, identify vulnerabilities, and exploit a vulnerable program with a code example. Disclaimer *: This tutorial is for educational purposes only. Exploiting vulnerabilities without authorization is illegal and unethical. This information should be used to learn about security vulnerabilities and how to prevent them. Prerequisites * basic C programming knowledge * familiarity with pointers, arrays, strings, functions, and the stack is essential. * understanding of assembly language * while not mandatory, a basic understanding of assembly language, especially x86/x64, will greatly aid in debugging and exploit development. Linux environment * a Linux environment, example Ubuntu, Kali, is recommended for development and testing. *GDB, GNU debugger essential for debugging and analyzing the program's behavior. Python, optional helpful for writing exploit scripts. Disable ASLR, address space layout randomization temporarily disable ASLR on your system for easier debugging. This is for learning purposes only and should never be done in a production environment. Run sudo sysctlw kernel.randomize_va_space equals 0 in your terminal. Remember to re-enable it after you are done. Sudo sysctlw kernel.randomize_va_space equals 2. * compile without stack protection and pi * use fno stack protector no pi when compiling your code. Again, this is for learning purposes only and should never be done in a production environment. What is buffer overflow? A buffer overflow occurs when a program writes data beyond the allocated boundaries of a buffer. This can overwrite adjacent memory regions, potentially corrupting program data, crashing the application, or, in the worst case, allowing an attacker to execute arbitrary code. What is ZAP compiler and how does it affect buffer overflows? ZAP is a specialized compiler designed to improve the reliability and security of C programs. It does this through several techniques, including automatic bounds checking ZAP instruments code to check array and pointer accesses for out-of-bounds writes and reads. If a bounds check fails, the program aborts with a clear error message, preventing exploitation. Stack protection ZAP often includes stack protection mechanisms to prevent overwriting return addresses. Why study buffer overflow with ZAP when it has protections? While ZAP's protections are effective, understanding how buffer overflows work in ZAP-compiled programs is valuable for several reasons. 1. Understanding underlying concepts * learning how ZAP prevents overflows helps solidify your understanding of the vulnerabilities themselves. This knowledge is transferable to other systems and languages. 2. Circumventing protections. For educational purposes, exploring potential weaknesses in ZAP's defenses can improve the overall security posture. Note, this should only be done in controlled environments and with ethical considerations. 3. Outdated or weakly configured systems * not all ZAP implementations are created equal. Older versions or misconfigurations might have weaknesses that can be exploited. 4. Complex scenarios * in complex applications, there might be subtle ways to bypass ZAP's protections or exploit other vulnerabilities in conjunction with buffer overflows. 5. Research and development * security researchers need to understand ZAP's defenses to develop new protection mechanisms or find novel vulnerabilities. Memory layout in a ZAP compiled program, simplified. While the specific details of ZAP's memory management can vary depending on the version and configuration, here's a general overview. Asterisk text segment. Text contains the executable code of the program. Read-only and often protected. Asterisk data segment. Data. BSS contains initialized and uninitialized global variables, respectively. Asterisk heap. Asterisk dynamically allocated memory used for malloc, calloc, etc. Asterisk stack. Asterisk used for function calls, local variables, and return addresses. ZAP often employs stack canaries, also known as stack cookies, to detect buffer overflows. Identifying buffer overflow vulnerabilities in ZAP compiled programs. Asterisk 1. Code review. Asterisk carefully examine the source code for functions that handle user input, especially functions that copy data into fixed-size buffers. Look for functions like asterisk strcpy, strcat, gets, sprintf, scanf, without length limitations, mempy, strncpy, when used incorrectly. Asterisk custom functions that perform similar operations. Asterisk functions that perform pointer arithmetic without bounds checking. 2. Fuzzing. Asterisk use fuzzing tools, like AFL, libfuzzer, to automatically generate random inputs and test the program for crashes. Fuzzing can quickly uncover potential buffer overflow vulnerabilities. 3. Static analysis. Asterisk use static analysis tools to scan the source code for potential vulnerabilities. These tools can identify code patterns that are likely to lead to buffer overflows. 4. Dynamic analysis. Asterisk run the program under a debugger, GDB, and observe its behavior while providing different inputs. Set breakpoints at critical points in the code to track memory accesses and buffer boundaries. Example code, vulnerable program. Compile the code, important, disable security features for learning. Explanation. Asterisk no stack protector, disables stack canaries, which normally prevent stack-based buffer overflows. Do not use in production. Asterisk no pi, disables position-independent executable, which randomizes the base address of the executable in memory. Do not use in production. Asterisk O vulnerable, specifies the output executable file name. Exploiting the vulnerability, step by step. 1. Analyze the program with GDB asterisk. Asterisk run GDB vulnerable. Asterisk set a breakpoint at the strcpy function within copy_string, break copy_string. Asterisk run the program with an input string, example run. Asterisk when the program hits the breakpoint, examine the stack, info stack or BT, backtrace. The stack frame will show the memory addresses of asterisk buffer, the fixed size buffer in copy_string. Asterisk the return address, the address to which the program will return after copy_string completes. Asterisk the saved frame pointer, EBP/RBP the previous stack frame's base pointer. To determine the offset asterisk. The goal is to overwrite the return address on the stack. We need to determine how many bytes of input it takes to reach and overwrite it. Asterisk use a pattern string to identify the offset. Create a unique pattern of bytes, example using pattern create 200 in GDB with the GEF or PWNDBG plugin. Feed this pattern to the program as input. Asterisk when the program crashes, Due to the overwritten return address, GDB will show the invalid address that was written to the return address. Use the pattern offset command, if using GEF or PWNDBG, or manually inspect the stack to determine the offset. For example, if the program crashes and the return address is overwritten with 0x41414142, which is BAAA in ASCII, then find the offset of BAAA in your pattern. In this simple example, the offset will be 32 plus 4, as the buffer size is 32 and the return address is 4 bytes, on a 32-bit system, 8 bytes on a 64-bit system, away from the buffer's end. Alternatively, you can examine the stack in GDB by setting a breakpoint just before the RET instruction of the copy_string function. You'll need to disassemble it using disascopy_string. Examine the stack using x/40x$sp to display the stack contents in hexadecimal. By carefully observing the stack, you can determine at which offset the user input begins to overwrite the return address. 3. Craft the exploit ***. The exploit will consist of the following parts. Padding a string of bytes to fill the buffer up to the return address. Return address the address of the code you want to execute. This could be the address of a function, example system/bin/sh, to get a shell. The address of a ROP gadget, explained later. 4. Finding the address to overflow with asterisk. With ASLR disabled, as described above, only for educational purposes, you'll need to find an address to put into the buffer that, when executed, will allow you to take control of the system. A typical approach in buffer overflows is to inject shellcode into memory, and then overwrite the return address with the address of the shellcode. However, this is complex, requiring careful placement of the shellcode and ensuring it's executable. A simpler approach, again, for learning, when ASLR is disabled, and you've disabled stack protection, is to use the address of the system function combined with the address of a string containing /bin/sh. Here's how you would do that. A. Find the address of system, asterisk. Run GDB vulnerable again. In GDB, this will print the memory address of the system function. Record this address. B. Create a string with /bin/sh asterisk. Modify the vulnerable.c file to include a global string containing /bin/sh. Recompile the vulnerable.c file with the same flags, gcc fno stack protector no pio vulnerable.c. C. Find the address of the /bin/sh string asterisk. Run GDB vulnerable. In GDB, this will print the memory address of the shell_string. Record this address. 5. Python script to generate exploit, example. Explanation of the Python script asterisk. System_address and bin_sh_address, replace these with the actual addresses you found in GDB. Offset, the offset you determined earlier. Padding, creates a string of A characters to fill the buffer. Struct.pack, q, address, packs the address as a 64-bit, q, little-endian, integer. Important for x64 architecture. Use I for 32-bit architectures. The exploit payload is constructed to call system/bin/sh. We also push a dummy return address to the stack, to ensure correct stack alignment. 6. Run the exploit asterisk. Save the Python script, example exploit.py. Run the script and pipe the output to the vulnerable program. If everything is correct, you should get a shell. Important considerations Asterisk address space layout randomization, ASLR randomizes the memory addresses of libraries and the stack, making it harder to predict where code and data will be located. You need to disable ASLR for this simplified example to work consistently. In a real-world scenario, you'd need to find ways to bypass ASLR, such as using information leaks to learn the base addresses of libraries or using return-oriented programming, ROP. Asterisk data execution prevention, DEP/NX DEP/NX marks certain memory regions, like the stack, as non-executable, preventing the execution of code injected into those regions. You might need to use techniques like return-oriented programming, ROP, to bypass DEP/NX. Asterisk stack canaries. Asterisk stack canaries are random values placed on the stack to detect buffer overflows. If a canary is overwritten, the program will detect it and terminate. The FNO stack protector flag disables canaries. Asterisk return-oriented programming, ROP. ROP is a powerful technique used to bypass DEP/NX. It involves chaining together snippets of code, gadgets, that already exist in the program or libraries to perform the desired actions. ROP is beyond the scope of this introductory tutorial but is essential for exploiting more complex vulnerabilities. Return-oriented programming, ROP, a brief overview. When DEP/NX, data execution prevention/no execute, is enabled, you can't directly execute code you've injected into memory, like shell code on the stack. ROP is a technique to circumvent this. It involves chaining together small sequences of machine instructions, called gadgets, that are already present in the program's executable or loaded libraries. Each gadget typically ends with a RET instruction, which transfers control to the next gadget on the stack. By carefully crafting a sequence of gadgets on the stack, you can achieve arbitrary code execution without injecting and executing new code. Key steps in ROP exploit development. 1. Identify gadgets. Use tools like ROP gadget or RP++ to search the executable and loaded libraries for useful gadgets. Common gadgets include *popreg, RET, pops a value from the stack into a register and then returns. Used to load values into registers. *mov reg1, reg2, RET, moves the value from register reg2 to the memory location pointed to by register reg1. Used to write data to memory. *call reg, calls the address stored in the specified register. Used to execute a function. To build the ROP chain. Carefully construct a sequence of gadgets on the stack to perform the desired actions. For example, to call system, /bin/sh, using ROP. Find a gadget to load the address of /bin/sh into a register, example using popreg, RET. Find a gadget to load the address of system, into another register. Find a gadget to call the register containing system. 3. Place the ROP chain on the stack. Overwrite the return address with the address of the first gadget in the chain. The rest of the chain will follow on the stack. Example, conceptual, simplified ROP chain. Let's say you have the following gadgets. 0x400100, property, RET, pops a value from the stack into the RET register, which is the first argument to a function on x64 systems. 0x400200, call racks, calls the address stored in the racks register. You want to call system, /bin/sh. Let's say *system is located at 0x7ffff7012345. */ben/sh is located at 0x7FFFF7B12345. Your ROP chain on the stack would look like this, assuming you've already overwritten the return address. When the RET instruction is executed after overwriting the return address, it will jump to 0x400100, property, RET. This pops 0x7FFFF7B12345, the address of /ben/sh, into the RET register and then returns. The next instruction executed will be at 0x400200, calling system, /ben/sh, effectively giving you a shell. Important ROP caveats **** finding gadgets *** the availability of suitable gadgets depends on the program and its loaded libraries. *** stack alignment *** ROP chains often require careful stack alignment to ensure that gadgets function correctly, especially on 64-bit architectures. Complexity ROP can become very complex, especially when dealing with more sophisticated protections. Limitations of this tutorial simplified example the example program is intentionally simple and lacks many common security features found in real-world applications. No ASLR/DEP bypass This tutorial does not cover techniques for bypassing ASLR and DEP/NX, which are crucial for exploiting vulnerabilities in modern systems. ZAP specific details The specific details of how ZAP manages memory and implements its security mechanisms can vary depending on the version and configuration. Mitigation strategies, general security practices. Input validation Always validate user input to ensure it conforms to expected formats and lengths. Bounds checking Use safe string manipulation functions like strncpy, tinprintf, and fgets and always provide length limits. Address space layout randomization ASLR enable ASLR to randomize the memory addresses of libraries and the stack, making it harder for attackers to predict memory locations. Data execution prevention DEP/NX enable DEP/NX to prevent the execution of code in data regions of memory, such as the stack and heap. Stack canaries enable stack canaries to detect buffer overflows on the stack. Compiler protections use compiler options like Stack Protector All to enable stronger stack protection. Static and dynamic analysis use static and dynamic analysis tools to identify potential vulnerabilities in your code. Regular security audits conduct regular security audits to identify and address vulnerabilities. Principle of least privilege grant users only the minimum necessary privileges to perform their tasks. Keep software updated regularly update your operating system, libraries, and applications to patch known vulnerabilities. Conclusion Buffer overflows are a serious security vulnerability that can lead to arbitrary code execution. Understanding how these vulnerabilities work, even in systems like ZAP that have built-in protections, is crucial for writing secure code and protecting your systems. This tutorial provides a foundation for further exploration of buffer overflows and other security vulnerabilities. Remember to always practice ethical hacking and use this knowledge for defensive purposes. Continue your learning by exploring ASLR bypass techniques, like information leaks, return-oriented programming, ROP, and advanced exploitation methods.